JWST looks at the next planet in the TRAPPIST system. Could we detect colliding supermassive black holes and hot Jupiters that flew close to their stars? All this and more in this week's Space Bites. It's time for the next episode of the JWST TRAPPIST Spectacular. Of course, the TRAPPIST-1 system is this incredible red dwarf star with 7 Earth-sized worlds orbiting around it, several of which, maybe 3, maybe 4 planets are in the habitable zone. And this is the ideal place for JWST to focus its instruments. It's the perfect machine. It's the perfect target. Let the science roll. And of course, we are getting this drip, drip, drip of science results. We already learned about TRAPPIST-1b, which is the closest planet to the TRAPPIST star, and it was very boring, probably like some kind of super Mercury. But all hopes were on the second planet. Astronomers were hoping, based on its distance and orbit, that it would be an analog to Venus. It would have a thick carbon dioxide atmosphere, and it would allow us to get a better sense of how planetary systems form. Is Venus the normal outcome in a planetary system? So JWST made its observations, and astronomers were looking for absorption in 15 micron light, and this is in the infrared spectrum. Carbon dioxide absorbs this kind of light, and so if the planet looks one way in other wavelengths, but then looks fainter in this 15 micron wavelength, then you can assume there's a lot of carbon dioxide that is absorbing the light and dimming it from our perspective. No luck. So JWST made the observations, and the planet didn't dim appreciably in that wavelength, and that leads astronomers to believe that, no, it does not have a thick carbon dioxide atmosphere. It could still have a thin carbon dioxide atmosphere, like something that is outside the bounds of what JW is able to see, or maybe it is like another super Mercury, so another rocky world. This is the second planet, and there's still a bunch more to go. And with the next planet, things get exciting because in theory, TRAPPIST-1d is the first of the planets that is potentially within the habitable zone around the TRAPPIST-1 star. And so, like, in the perfect world, we get to see water vapor and oxygen and ozone and carbon dioxide and all these other chemicals in the atmosphere of this world, or we see nothing. And it's just another super Mercury, and on to the next. So stay tuned for the next thrilling episode of what's going on with those planets at TRAPPIST-1. Maybe there's a way to detect supermassive black hole mergers. At this point, I'm sure you're quite familiar with the idea that gravitational wave observatories can detect colliding black holes, but they can only detect the stellar mass black holes, so the ones with dozens of times the mass of the sun. They can't detect the ones with millions or even billions of times the mass of the sun mashing together. And that seems surprising. Like, you would expect that the most massive black holes would be the ones that you would find first, and then you'd find the smaller ones. But the problem is that the supermassive black holes are so big, their event horizons are so large, that as they merge, it all unfolds very, very slowly. And so the waves that ripple out from that event, although they are powerful, they are very long wavelength, too long for LIGO to be able to detect them. It's looking for chirps, not this sort of extended groan that happens when supermassive black holes merge. But there's another way, and this is a technique called pulsar timing. And so what astronomers have done have mapped out many, many pulsars in our environment. Specifically, they're looking for the millisecond pulsar. These are ones that are spinning hundreds of times a second, close to 1,000 times a second, and releasing these regular pulses of radio waves. It's so perfect that astronomers are able to use this as like a natural clock. To propose you could use this for celestial navigation. If you go through a wormhole and appear somewhere randomly in the Milky Way, you could use pulsars to figure out where you are. And so as gravitational waves move past these pulsars, they will shift them a little bit back and forth. And so this will change the wavelength of the light that we see coming from the pulsar. And so over a lot of observations, over decades of time, astronomers are hoping that eventually these pulsar beacons will start to reveal supermassive black hole collisions in the vicinity. And so astronomers did a long-term study where they looked through over 12 years of pulsar timing data with a survey called NanoGrav. And they failed to turn up any billion mass black hole mergers within 300 million light years of us. So that's not surprising. Like 2 billion plus supermassive black holes coming together within 300 million light years of Earth is not a very common occurrence. But as the sphere gets larger and larger, then you should anticipate more and more of these collisions to start being detected. It's only been 12 years of pulsar timing data, and so astronomers are just going to keep watching and waiting and listening. And over time, as more and more data comes in, eventually we should start to get those hints of those first supermassive black holes, either farther away or more massive or less massive. At some point, we will get this confirmation that everyone suspects that supermassive black holes are merging together. An echo from our own supermassive black hole. Speaking of supermassive black holes, there is a supermassive black hole at the heart of the Milky Way, which astronomers call Sgr A star. And this black hole is relatively quiet today. Every now and then, astronomers detect a slight burst of radiation, X-rays, coming from a snack that the black hole is eating, like probably like a small cloud of gas and dust, something with a couple of times the mass of the Earth. But astronomers have figured out that about 200 years ago, a fairly significant meal was consumed by the black hole and released a giant blast of X-ray radiation. Now, I'm sure you're saying, well, how did they figure this out 200 years ago before there were space telescopes, before we could detect X-rays coming from supermassive black holes? And obviously you understand that the supermassive black hole is tens of thousands of light years away, and so any event that we see happened in the past. I get it. I've talked about this many times before, so go ahead and, go ahead, comment, and we'll have lively conversations about it. But, so how did astronomers work out that this event happened? And so what they saw was the echo. And so you can imagine when this meal was consumed by the supermassive black hole, you got this expanding sphere of X-ray radiation. Some of it would have come our way, and if we did have space telescopes back in the day, we would have seen it. But others sort of started to permeate the surroundings around the black hole. And some of that is clouds of gas and dust that are within 200 light years of the black hole. That gas reflected the X-ray radiation in our direction and in all directions. And so with a combination of X-ray satellites, you had the XMM Newton, you had the Chandra X-ray, you had the IPXE, you've got all these different space telescopes that were able to detect this signal of X-rays coming from the region around the black hole, and then they were able to calculate when this blast happened. But what actually caused it? And right now astronomers don't know. Like the black hole ate something. How much it ate, how long it consumed it for, was it quick, was it a star, was it a cloud, was it a planet? We don't know yet, so stay tuned for more details. Starlink Generation 2 is dimmer. Astronomers have been extremely concerned about the brightness of the Starlink satellites, and there are now thousands and thousands of them in space, and eventually there will be tens of thousands of satellites just from Starlink, not to mention all of the other constellations. So needless to say, this is very worrying for the field of astronomy as you get more and more satellite trails passing through your images. Like, it's believed that 30% of images from the Vera Rubin telescope are going to have satellite trails passing through them at any point. So the effect is going to be significant. And Starlink has rolled out a new type of satellite. They're called Generation 2, and they have about 4 times the surface area of the Generation 1 satellites. And so this was very worrying because you've got much larger satellites. It's expected they're going to be much brighter. But good news, they are not brighter. In fact, they are dimmer than the Generation 1 satellites. So a team of astronomers have gone and categorized both the Generation 1 satellites and the Generation 2 satellites. And they also looked at sort of when the satellites were initially launched and as they were making their way up from their launch trajectory into their final stable orbits where they go into production. And they found that initially, yes, the satellites are brighter. You get this brighter train of satellites passing overhead. But once they reach their final production orbit, then they shift their angle, and they also have a special non-reflecting material that they deploy that decreases the brightness of the satellite. And so they found, in fact, that the overall brightness of this generation 2 are dimmer. And this could turn around in the future because Starlink is planning an even larger version of these satellites when the SpaceX Starship finally comes online and is capable of launching heavier payloads. And so we could see that the very limits of what the dimming technology is able to do gives up, and these satellites get bigger and brighter. And so right now, on average, the Starlink satellites are about visual magnitude 8, a little brighter than magnitude 8, which is well beneath what a human being can see with the unaided eye. But the problem is that over time, as you get more and more of these satellites, you get a kind of light pollution that is planet-wide. It's as if there are city lights everywhere around Earth. And even if you try to move one of your observatories to a place that is really far away from a bright city, there is this increasing sky glow that's going to affect their observations. And we don't know what the impact of that is going to be. And so the bottom line is that we're going to see more and more of this tension, more of these issues as we move forward into the future. And my hope, and I've mentioned this many times before, is that people just coordinate better to make sure that as much astronomy can be done, and at the same time that people can communicate at remote places on planet Earth. But it's what I hope. Like, why can't I just keep asking people to get along and be nice and talk with each other and mitigate these problems so that we can have the wonders of communication anywhere on planet Earth and the ability to do astronomy? Like, is it too much for me to ask this to happen? But maybe we'll be able to deal with all of the space junk. And so a new satellite has been proposed by a company called Astroscale. Now, Astroscale has been in the news before. They launched a prototype satellite several months ago called ELSA-D, and this was a space junk cleaning robot mission, but with a caveat. So this tiny satellite took its own test mass with it to space, its own friend, and then it practiced different ways of matching orbits, grabbing onto the satellite payload, then releasing it, and then docking again. It uses magnets to be able to actually clamp on to the target. But they're planning a more ambitious version of this called ELSA-M. And so what ELSA-M will do is fly to space, be given a target. It will approach the target using a combination of chemical and ion thrusters, and then it will match orientation. So whatever the speed is, as well as whatever tumble rotation its target is making, then it will use this magnetic clamp to be able to grab onto its target. And then it will give it a kick in the opposite direction to slow it down and cause it to re-enter the Earth's atmosphere sooner than it would normally take. And then it can move on to another target. And so theoretically, each one of these ELSA-M satellites could deorbit many spacecraft on their own. And maybe they could be refueled down the road, and then they could just keep going and going and going and slowly cleaning up the increasing problem of space junk. So we'll look forward to this test in the future, and we'll see if this is going to work. Now, after every episode of Space Bites, we put up a vote in the community tab so that you can tell us which of the stories you thought was the best this week. And so last week, not surprising, was the discovery of phosphorus at Enceladus, one of the key chemicals needed for life found on Enceladus. This is exciting. And it's the one I would have voted as well. So thanks everyone for voting. We'll put up the vote for this week's stories in a while, and then you can go ahead, see that in your feed, give it a vote. If you aren't, make sure you're subscribed to the channel, and then you'll see when the vote comes up. 2 hot Jupiters that got too close. We've got a couple of stories here that are related, so we've kind of mashed them together because they're both really interesting. And so the first image is this exoplanet. It's a hot Jupiter that got too close to its star. The planet has about 0.68 the radius of Jupiter, but it's about 4 times the size of Jupiter. And this is because it is incredibly hot. Its surface temperature is 5,700 Celsius, which is hotter than the surface of the sun. So it is way too close to the star. And this temperature is so hot that it has caused its outer atmosphere to evaporate away into space, creating this enormous tail. And the tail stretches 53 times the length of the radius of the planet. And so the planet is kind of swimming in this soup of its own helium atmosphere, and the star is continuing to blast it with enormous amounts of radiation. This planet won't be around forever. But this process has helped astronomers answer like another long-standing mystery in astronomy. So there's this star called FU Orionis, or FU Ori. And astronomers first figured out there was something weird going on with the star, like in the early 1900s. It started out at magnitude 16 and then suddenly brightened to magnitude 9. And each number in magnitude is a 10 times brightening. So to go from 16 to 9 is many orders of magnitude of brightening. What could cause a star to brighten that much? Well, new evidence seems to be that this is a young, hot star, and it has a hot Jupiter orbiting around it, and it's the same situation. There's so much radiation pouring off the star that it has caused the outer atmosphere of a newly forming hot Jupiter planet around it to puff out its atmosphere. The atmosphere is being pulled in by the star into an accretion disk around the star, and that's causing the star itself to brighten up. Again, this is a very young star, young planet. I don't like this planet's chances of surviving very long. Another strange discovery from the Parker Solar Probe. Now, we've been focusing on the Parker Solar Probe's observations of the sun, but in fact, this week Parker was able to help figure out another long-standing mystery in astronomy. And this is, what is the source of the Geminid meteor shower? Now, the Geminids are the brightest, most active meteor shower in the year. Now, they're in December, so for those of us in the Southern Hemisphere, it's really hard to justify going and sitting outside all night in sub-zero temperatures watching meteors. I like the Perseids. They come in August, and so you just lie outside in a lounge chair and watch meteors overhead. But the Geminids are better, no question. And astronomers have figured out that the source of the Geminid meteor shower is an asteroid called 3200 Phaethon. And this is weird because most meteor showers come from comets, and so it's very strange that a meteor shower comes from an asteroid. And astronomers assumed that there was just this common envelope of dust around the asteroid that's just forming this ring where the asteroid is orbiting around the sun. And we saw something very similar to this. Like, think back to what happened when NASA's OSIRIS-REx mission came up to asteroid Bennu. It started to get pelted by sand as it got closer and closer to the asteroid. And so there is this material that's being lifted off the surface of the asteroid and flying off into space. And so Parker Solar Probe was able to make observations of the dust trail in the region around asteroid Phaethon. And that's because it's just getting close to the sun. It was in the area. So they figured, why don't we take a look? And what they found is, no, it is not some kind of standard, just regular trail of dust that's filling up the area. In fact, there are blobs that seem to be caused by some kind of catastrophic event. So we see this meteor shower because at some point, asteroid 3200 Phaethon was smacked by another asteroid and it released a fairly large cloud of material that we are passing through on a regular basis once every year. If you enjoy our interviews, we took a couple of weeks off, but now we're back. We've got a lot of interviews. In fact, yesterday, I think I just asked 5 different people for interviews, so hopefully some of them will pan out. But you know, I have said this several times before that I think the interviews are some of the best work that we do here on the channel. It is the journalism. It's where we are reaching out to the scientists, the astronauts, the Nobel Prize winners who are doing this work, and we're hearing directly from them. And I'm able to ask the questions to them that you ask me. And so I'm like this pipeline from you to me to scientists back to you. And so if you haven't watched the interviews, I do recommend them. I mean, you can learn about turning the sun into a giant lens that will let us see a planet with a megapixel resolution. You can learn about ways to get closer and closer to the speed of light. You can learn firsthand what it was like to build and operate the James Webb Space Telescope. So if you haven't already, we've got a playlist. You can go back in time, and they're evergreen. Some of them are just classics. So definitely go and check out our interviews on the channel. It's time for more images and videos. And so let's start with this really cool picture that comes from NASA's Juno spacecraft of Jupiter. And this looks like your standard Juno picture. I've seen a million of them before. And this is older data. This came from a flyby that Juno did back in 2020. But if you look carefully, there is a bright spot in the cloud tops of Jupiter. And this is lightning. Now, the image was noticed by Kevin Gill, who is one of my favorite citizen scientist image processors, and he was able to take this image and clean it up and really highlight that lightning activity in the upper cloud tops of Jupiter. And what's interesting about Jupiter is that here on Earth, lightning activity tends to happen closer to the equator. But on Jupiter, the lightning happens closer to the poles, and astronomers think it has something to do with the composition of the atmosphere. But it's very cool to be able to see a giant lightning storm on another planet. And the next set of images come from the European Space Agency's Bepi-Colombo mission. These are images that it took during its third flyby of Mercury. Now, Bepi-Colombo's eventual destination is Mercury. It's like, didn't it already get there? Well, why is it going to do a flyby? Well, the problem is that Mercury is one of the hardest places to reach in the solar system. You need to shed an enormous amount of velocity to be able to go into orbit around Mercury. And the way you do that is with gravitational assists, but in the opposite direction. So while you might use a gravitational assist to go past Jupiter to go faster, when you go around Mercury, you use it to go slower. And eventually, after 6 gravitational assists around Mercury, it will finally be going at a close enough velocity to the planet that it can use its thrusters to finally go into orbit. What's cool about this image is we got some of the illuminated portion of Mercury, but also some of the night portion of Mercury. And so astronomers are able to compare and contrast what it looks like during the day and during the night. And of course, when it finally arrives in its final mapping orbit, it'll be able to just take non-stop pictures of Mercury from every perspective. And finally, we got this amazing simulation of carbon dioxide emissions coming from North and South America. And so this is made up of an enormous amount of data collecting instruments that NASA has. They have satellites, they have ground stations, they have ways to detect both the amount of carbon dioxide that's being released as well as the amount that's being absorbed at various places around the world. And so you can see, like, this is what it would look like if you could see carbon dioxide with your eyes, if it wasn't colorless. And so you can see that a lot of carbon dioxide is released from North America. Specifically, you can almost see this line where it sort of splits up the United States. You can see where the vast majority of the carbon dioxide is coming out. And you can see how this stuff swirls around and heads out around the entire northern hemisphere. And then you can also see places in green where plants are releasing carbon dioxide, as well as places in blue where the oceans are releasing carbon dioxide. And then you can also see how this material is being absorbed again, because carbon dioxide goes through this annual cycle where you get more carbon dioxide released and then more absorbed as the plants are continuing to grow. And so it's an astonishing visualization of what this carbon dioxide release looks like, with a big emphasis on what we as human beings are doing to release it. So it's wonderful and terrifying. It's an amazing visualization. I hope you enjoyed these news stories. Now you can do a deep dive into any one of them. We have the sources and links for everything that I talked about here in the show notes down below. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I read every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Antonio Lofi Lara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltinan, Modzo, George, Jeremy Matter, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us. All right, that was all the news that we had today. We'll see you next week.